Imagine flying hundreds of feet above the ground in a machine that literally cannot glide. Now imagine that the only thing keeping its giant spinning blades attached is one single metal nut. Not a system of backups, not a second safety net, just one piece of threaded steel. Helicopters don't soar like airplanes. They stay up by smashing air downward with incredible force. And for decades, the lives of pilots and passengers depended entirely on a single fastener with a nickname so dramatic it sounds like a movie title, the Jesus Nut. Hi, welcome to Why Explained. Today we're going to unravel the engineering mystery behind the one tiny part that kept helicopters in the sky, and why modern aircraft designers eventually decided that one was not enough. Most people assume aircraft are designed like action movies, layers upon layers of backup systems. If one engine fails, there's another. If a computer crashes, a second one instantly takes over. Airplanes are basically flying bundles of redundancy. So naturally, you'd expect helicopters to work the same way. But early helicopter design had a very different philosophy. Instead of multiple overlapping safety systems, some critical components were built around absolute strength. If that part held, everything worked. If it didn't, nothing else mattered. In engineering, this is called a single point of failure, and it's exactly what it sounds like. One part, one job, total responsibility. In the case of early helicopters, especially during the 1960s, that responsibility sat right at the very top of the rotor mast. A single retaining nut held the entire spinning rotor assembly to the aircraft, and if that nut came loose mid-flight, there was no backup plan. To understand why that one nut mattered so much, we need to understand how helicopters actually fly. Airplanes glide forward. Their wings generate lift as air flows across them. Even if the engines fail, they can still glide for miles. Helicopters? Not so much. Helicopters stay in the air by spinning massive blades at high speed, forcing air downward. Newton's third law kicks in. Push air down, and the aircraft goes up. Simple in theory, violently mechanical in practice. Those spinning blades are attached to something called the rotor head, and the rotor head is mounted to a vertical shaft known as the rotor mast. At the very top of that mast, holding everything together, sat the main rotor head nut, what soldiers later nicknamed the Jesus Nut. Its job was brutally simple: keep the entire rotor assembly attached to the helicopter. If it failed, the spinning blades would detach instantly, and without spinning blades, a helicopter is just gravity. So how do you prevent a heavily vibrating machine from shaking loose a threaded metal fastener? You over-engineer it. The nut was torqued down with tremendous force, but that wasn't enough. Engineers added a thick steel cotter pin or heavy-duty safety wire through the nut and mast. For the nut to spin off, it would first have to shear through solid steel. And before every flight, pilots or engineers didn't just glance at it, they physically touched it, checked the pin, confirmed it was intact. It became ritual. Because when one part holds everything together, you don't rely on hope. You rely on inspection. Historically, the nut almost never failed. The safety system worked exactly as intended. The real risk wasn't poor design. It was the terrifying idea that so much depended on so little. Here's the surprising part. The Jesus Nut was not a design mistake. It was actually an engineering success. Despite the dramatic nickname, documented failures of the main rotor head nut were extremely rare. The safety wire system worked. The inspections worked. The metallurgy worked. In many cases, helicopters failed because of combat damage, fuel issues, or other mechanical problems, not because that single nut gave up. So if it worked, why change it? Because engineering doesn't just aim for usually safe, it aims for safe even if something goes wrong. As helicopter technology advanced, designers began eliminating single points of failure altogether. Instead of relying on one massive nut, modern rotor systems use multiple heavy-duty bolts. If one bolt cracks, the others redistribute the load. Think of it like replacing a single rope holding a bridge with a bundle of cables. The bridge doesn't collapse if one strand snaps. In aircraft like the Black Hawk or Apache, redundancy became the rule. Not because the old design failed often, but because depending on one critical part feels like betting everything on a single coin toss. And the term Jesus Nut survived. Today, Engineers sometimes use it informally to describe any single component that can bring down an entire system, whether it's in aviation, software, or even power grids. It's a reminder that sometimes the smallest piece carries the biggest responsibility. So what's the real lesson of the Jesus nut? It's not just about helicopters, it's about design philosophy. For decades, one small piece of metal held together thousands of pounds of spinning machinery. And it worked. Not because it was magical, but because it was engineered, inspected, and respected. But modern engineering learned something deeper. Strength is good. Redundancy is better. Today's helicopters distribute risk across multiple components, not because the old nut constantly failed, but because eliminating single points of failure makes systems more resilient. And that idea applies far beyond aviation. From software servers to suspension bridges, engineers now ask one crucial question. If this one part fails, what happens next? Sometimes the biggest machines in the world depend on the simplest pieces, and sometimes progress isn't about building stronger parts. It's about making sure no single part carries the entire weight alone. Science is full of strange little details hiding in plain sight. If this one surprised you, Why Explained has plenty more waiting. And as always, stay curious.